Hello everyone, there's going to be a short 2-problem quiz tomorrow over questions like this. That's why we're going to practice one today. And yes, my remote students, you will have to join Zoom to work on this. All right, so here, and you could just use Desmos, that's all you need. Make sure you look at your homework problems though. But here we're given f of x is equal to 2x to the fourth minus 5x cubed plus x squared minus x plus 4. We want to answer the following questions. And again, these questions do not take too long to answer. A, how many complex zeros does this function have? Well, this is related to the degree. So here we would say, so maybe even on the quiz tomorrow, I might ask you for the degree, but we would answer saying the degree is equal to what? The largest exponent, so it's 4. So we would expect four complex zeros. How many relative extrema do we expect the graph of the function to have? This is the degree minus 1. So that would give us 4 minus 1, or 3. We would expect 3 relative extrema on the graph. So now what I want you to do is pause the video and actually go ahead and graph this on Desmos and answer the following questions. How many real zeros does a function actually have? And then use that to answer how many imaginary zeros does the function have. Part D, find the real zeros of the function. And then state the relative extrema and where they occur. Remember how to answer that. So pause the video, graph that, answer those 3 questions, and then resume playing. All right, and if you need more time, pause the video again, but I'm going to go to Desmos to show how I have this graphed. So this is what's nice. So notice Desmos already gives you the points that we're seeing here. So if you notice, we've got these 2 points only. So those are the only 2 real x-intercepts or real zeros. So to go back to answer this, we have 2 real zeros. Now the total of complex zeros was 4. So if we only have 2 real zeros, that means we have 2 imaginary zeros. These 2 numbers need to total the degree. So if we had 3 real zeros, we would only have 1 imaginary zero. Go ahead and find the real zeros of the function. So we go back to the graph. We only want the x values here. So 1.16. Now this Desmos should always round out to 3 decimal places, so that it really means there's a 0 after it, and a 2.184. So we're going to list them this way. The zeros are the 1.160 and 2.184 in the set brackets, not parentheses. Part E, state the relative extrema and where they occur. Now again, the way we can tell, this 4 is a point, but it is not a relative extrema. The way to be sure is our graph has to change from increasing to decreasing or decreasing to increasing. So if we take a look to the left of this point, our graph is decreasing and it's still decreasing. So we do not have a relative extrema there. We only have 1. Even though we expected 3, we only have 1, and it's a min. So we would say the relative min is y equals, let's go back to that, negative 2.733 when x is equal to the 1.774. All we have to state. Now, had there been another min, we would have mentioned it again, another statement. If had there been a relative max, we would have mentioned that. You need a statement for every min or max you see. Now, I do want to go back and talk about this point right here. That would be what? The y-intercept. So if I did ask another question, what is the y-intercept? It would be at 4. And you could see it graphically, or you just go to the very last number here, because if all the other x's are 0, you're left with that. So in this case, the y-intercept would be the ordered pair 0, 4, or just 4. All right, so let's go ahead next and take a look at the answers to yesterday's worksheet. So remember, any problem that had a part B, you had to expand it. And any time, like in 14, where we see an x-intercept of 0 show up on the graph, we just have a single factor of x. So please go ahead and take a look at these. Now, if you didn't have a negative sign, I just put it in 20 because of the direction, which means if you didn't have the negative sign, your graph just would have opened up in the opposite direction. And it wasn't necessary to put the negative. I just have that there. All right, and for the others, you had to sketch a possible graph. So please email me if you have any questions over 14 to 20. And again, these are all possible directions. So if you didn't have exactly what I have for 23, you could also come down through the -3, go up through the 1, turn and come back down through the 2. Those are the only two possibilities. But again, if you take a look at the function, make sure you have f of x equals or y equals. If you don't have that, it's not technically a function. And then we just expanded this. Now just to go over the expanded form, just to show you another example, I'm going to go ahead and multiply the last two together first. I have the x plus 3. Multiplying those two together will give me an x squared. Minus 1x minus 2x will give me a minus 3x and then a plus 2 at the end. Then I want to distribute the x into the trinomial, so we'll get an x cubed minus 3x squared plus 2x. Then we'll distribute the 3 in, so then we'll have a plus 3x squared minus 9x plus 6. So combining like terms, we end up with an x cubed. My 3x squares cancel out. 2x minus 9x is minus 7x plus 6. 24, you did not have to write that out in expanded form. We do have a double 0 at 3, so we write it as x minus 3 squared. Likewise, in 25, we have a double 0 at -2, so we would write it as x plus 2 squared. And again, I put a negative in front just because it opens down. You didn't have to have the negative. It is not wrong if you did not have that, because I could have drawn this going up as well. And take a look at 26 and 27. Again, both of these have x-intercepts at 0, so notice the single factor of x. And again, just let me know if you have questions. Okay, so our main idea for today is to start application problems. But before we do that, I just want to throw in this extra problem. Here I'm giving you a quadratic function in vertex form. If you notice the setup of it, this is already in vertex form. Let's go back to general form. So if you recall, general form is where we just have y is equal to ax squared plus bx plus c. So how do we do that? We've been practicing, and you guys were quizzed over taking from general form to go to vertex form. You can get there by completing the square or by using the HK method. So it's a little bit easier to go from vertex form to general form. All you have to do is what the problem says. Follow order of operations and expand this. So first, we want to square the x minus 5. So then this becomes y equals -3. And if it helps, write it out. So we have to multiply these binomials together first. Do not distribute. This is one big thing to avoid. We cannot distribute the -3 because exponents come before multiplication. So what we do is we leave the -3 out in front, multiplying these two together, we'll get x squared. We'll get a minus 10x in the middle, plus 25 at the end, and then plus 6. Now we distribute the -3. So we get a -3x squared plus 30x minus 75 plus 6. And then we could just add those together. So we get y equals -3x squared plus 30x. And then we'll get a minus 69. And then this is general form, so it looks like this. All right, so what you're going to need for today's problems is the worksheet I posted as a PDF. We're going to do 2 problems off of this together. You'll still need to use Desmos. All right, so we're going to take a look at problem 1. Notice it says the directions for all 9 problems. Make sure you do this on a separate sheet of paper. Clearly set up the solution to the problem. Identify what the variable represents, so we may have more than one variable. Solve and check by using our calculator, Desmos. Unless otherwise specified, round all final answers to the nearest thousandth. So question 1, some of these we may have to draw a picture for. An open box with no lid is to be constructed from a rectangular piece of sheet metal that is 10 feet by 15 feet. Equal size squares are cut out from each corner and the sides are bent, folded up to form the box. What is the length of the side of the square that will make the box with the largest volume? And what is that largest volume? So let's just start. We have a rectangular piece of sheet metal. So I'm just going to draw a rectangle out like this. And equal size squares are going to be cut out from each corner. So what's happening is when I cut these squares out, we're going to kind of get a perforated line here that we're going to fold up. So everything right in here, that's going to be the base of the box, and then the sides are going to come up. So looking at this from a side view, we'll have our box that folds up this way. So this flap right here is really this flap that's right here. So I know that this is X units long, X, what are we in feet? X feet long here, 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 and here. Now originally, this side measured, we'll say 10. But now we cut out X feet from either end, so we're only looking at this side. So again, really what was in purple was 10, but how can we write an expression to represent what I have here in green? If we cut out an X from each end, that would be 10 minus 2X. So we'll say the width of the box measures 10 minus 2X feet. Likewise, the original length of the box was 15, but now that we're cutting X out from either end, what's in green here is going to measure 15 minus 2X. So the length of the box measures 15 minus 2X feet. And then what's X? This is kind of wordy. X is the length of the side of the square that will make the box have the largest volume. So if we fold that up, isn't it easier to say X is the height? So we want to know what height. The larger we make the squares, that's going to be the height. So we want to know how large to make it so we maximize the volume of the box. So X is the height. So now we need to come up with a function. I'm going to call this V of X for volume. And if you remember, the formula for volume of a rectangular prism is just length times width times height, but all in terms of X. So V of X is going to equal, I'm going to put the height first, X times our width, which is 10 minus 2X, times our length, which is 15 minus 2X. So we did everything we said. We set up the solution on how we're going to get the solution. We had to draw a picture and label it. We labeled our variable, height was X, then our width was the expression 10 minus 2X, and our length was 15 minus 2X. So now go back to Desmos, clear out the graph you had in there, type this in. Now you could just call it Y. I don't know if Desmos will, it should accept a V of X, but you could just type in Y. So go ahead and type that in, and then we'll see how we can adjust our screen. All right, and pause the video if you need some more time. So notice how I just have mine typed in. Now we're looking for the max. So we need to climb up pretty far here. And again, do not try to just shift the graph. Let's go to the tool icon. And I just want to change my Y max here. So I should just be able to get rid of that. Now here's what I go off of. The two numbers, 10 times 15 is 150. So I'm going to go with that. And notice I could see my max right here. So that's going to be good enough. So click on that point. That's the ordered pair that we need to use to interpret our answer. So I'm going to go ahead and write that on with the problem here. So the ordered pair we get is 1.962, comma, 132.038. Notice how they're already rounded out to the nearest thousand, 3 decimal places. This is not the answer. This is the answer. We would say the max volume, answering both questions at once. Both questions are What is the length of the side of the square? So what's x? That will make the largest volume. And what is the largest volume? So we can answer both of those in one sentence. The max volume is the same as the y value, is 132.038. We're in feet, and volume would be cubic feet, when the height of the box is 1.962 feet. And again, x is the length of the side of the square, but that's a little wordy. We could just call it the height. This is our answer. This is just what we got from looking at the graph to help us interpret it. If you leave this as your answer, it will be wrong. All right, so let's try another one. Let's go to number 7. What's nice about this problem is they give us the function. All right, so in this problem, they tell us in business, one of the main ideas is to minimize costs while maximizing profit. An engineer for a particular company has determined that the total cost of manufacturing its parts is a function of the total number of parts produced. So here's our cost function. C of x is equal to 0.4x cubed minus 1.7x squared plus 1.1x plus 4.8. Where C, now pay attention to what C and the x values represent. C is the cost in thousands of dollars, and X is in hundreds of parts produced. Find the number of parts produced to the nearest whole number and the corresponding cost to the nearest dollar that makes the least cost. So right now, go to Desmos and type this in. Pause the video and do that. Okay, so let's see what you're coming up with. Now, if you still have the settings from the last graph in there, I'll show you what to change, because you might not get this picture right here. All you have to do, because in the last problem we took our y max up to 150, just make that back at 10, and then we should be good. Now we're looking for the least cost, so that's why I clicked on this point right here. So go ahead and click on that. It should have already been up there. Mine went away because I just clicked off to the graph there, off to the side. So this should be the lowest point, our relative min. So we're going to use that. So we're going to write down that ordered pair, but once again, that is not our answer. So we'll say that ordered pair is 2.461, comma 3.173. What are these numbers? This is X. This is the number of parts produced, but it's in the hundreds. So we need to multiply this by 100. This value is the total cost, but we need to multiply it by 1,000 because it's in the thousands of dollars. So this is how we answer our question. So this is the answer. The minimum cost, or the least cost, is, if I multiply this by 1,000, we're getting $3,173 when, now if we multiply by 100, we're only moving our decimal point over twice, and that's okay because it says to the nearest whole number for the number of parts produced. So that would be 246 parts are produced. That's it. All you have to need to know for this is obviously graphing this. They give us the function. Find that ordered pair for the minimum and interpret it. Take the first number, multiply it by 100. That's our X value. That's the number of parts. Take the second number, multiply it by 1,000. That's our cost. That goes first. So here the least cost is $3,173 when 246 parts are produced. All right, so off of today's worksheet, I just want you working on 2, 6, and 8. And like I said, tomorrow there's going to be a short quiz, 2 problems, just like our warm-up problem at the very beginning, finding zeros, the total number of complex zeros, real zeros, imaginary zeros, know the degree, know how to state the zeros, how to find the extrema, and the y-intercept as well. Let me know if you guys have any questions.